term grades, so we have to do it before.
Oh, that makes sense.
Yeah. We'll wait for a few minutes. Did you like the homework or the project?
I found it pretty satisfactory.
Yes. Well, I'm glad you do.
I'm just waiting for the next episodes.
Well, it's already out.
Yeah, as you see, it turned into how to get away with murder. Nobody's here.
David Welsh.
Sure.
There you go. Okay, we can start. So, the next assignment is up, and it's due soon. So I put it up sometime last week, and it should be due next Tuesday or Thursday, I forget. So this is basically one-dimensional advection, where you will use an upwind discretization in space, and you will just advect a very simple Gaussian profile. Okay? And the second part of this is do the same thing, but with a second-order upwind scheme. And for that, you're given that you can write the spatial derivatives as follows. Okay, so it's relatively straightforward, and it will probably not take too long to get there. But it's it's something you might never have done before, so you might have a lot of bugs. The next assignment, which I've put up, but it'll be available to you when you submit this, is on 2D advection. That is going to take some time. So start early on that one. Yeah, it's basically the same thing. You use periodic boundary conditions in 2 dimensions and do the advection with a given velocity field. But there's a lot more bookkeeping involved in it. Programming becomes more of a hassle. Okay. So let's see, what else? Do you have any questions from project? The previous one? All right, or current one?
Awesome, yeah.
Okay, and also we will probably have a few class cancellations on 3 dates. So I will confirm these and send out an announcement. Potential class cancellation on let's see, the first one is March 28th, April 11th, and April 18th. So April 18th, we have the ocean engineering senior design presentations. And if you can, go and take a look at the projects they have been working on. Okay, so I will confirm those dates and then send the announcement. Let's get back to what we were doing, which was, these are just notes from the previous class, so I'll just go over them quickly. You don't need to write them again. We were looking at the pressure-Poisson equation. When we do pressure projection, this U star star was the intermediate velocity field, which was not divergence free. And we figured out we would have to find the pressure in this manner and make the final velocity divergence free. Okay? And in 2D, we just wrote out the full equation. Everything here is known on the right-hand side, and all the pressure values are unknown on the left-hand side. And in 2D, this is just a 5-point stencil with up, down, left, right, and the center. And we have to solve this for each of the points in the domain. Okay. And then we said we will only take a look at this left bottom corner, and we were writing out the individual equations for different I and j values. Okay. And this was the full general equation. And we use the fact that we know the boundary conditions on the left and bottom boundary. We were given a Neumann boundary condition. dp dy is something, dp dx is something. Okay. And then we started writing out, okay, for I equal 1, j equal 1, we can either use dp dx equal the given value or dp dy equal the given value. You're free to use either one. And for I equal 2, j equal 1, we have the next value. So we can keep going like this, and for all j equal 1 points, we will have something very similar. Why did I write 0? Oh yeah, that's correct. So dp by dy equals 0. So for all subsequent I equal 3, j equal 1, and whenever we have a j equal 1, we will have something similar. 0. Basically, p I j plus 1 minus p I j over delta y equals 0. Okay. All right. So what happened after this? So after this, what we need to do is assemble all of this into a big matrix. Okay. So let's write that out. Let's see. Okay. So let's see, where should we do that? Okay. Let's put the pressure vector, the unknown pressure vector over here. And the first one will be, what will the first one be? Pressure at node. Do you know what I mean when I'm forming the matrix? It's the same thing you have done in your homework when you did implicit time integration. All the unknowns go in here. So the first unknown that I want is p1, 1. Okay. Even though I'm given the boundary condition, it's a Neumann boundary condition, not a Dirichlet one. So this p1, 1 is unknown. Okay. Then I will want to find out what p2, 1 is. So this is, I'm basically going through all the bottom boundary nodes. Okay. And so on. Okay. What happens next is we will move up to the second row, which will give us p1, 2. So we basically jumped from all of these points to now writing all of these points. J equal to p2, 2, p3, 2, p4, 2, so on. And the same for next row, p1, 3, p2, 3, so on. All right, so let's see what goes in the matrix here. Okay, so what is the first equation? Okay, which one do you want me to take, this or that?
Delta y.
Delta y, you want me to take this one? All the others are delta y's, right? So let's take this, the first one to be different to see how it will look different in the matrix. So let's see, this is p21, p11. okay, and there's a delta x, okay, so, okay, on the right hand side, let me put 5 delta x, okay, that comes from here, 5 delta x, and P21 minus P11, so P11 is to be minus 1 P21, okay, this, yeah, fine, it's 1 0 0 0 0 0, all of them zeros, okay. So it's basically minus P11 plus P21, which is what we have, minus P11 plus P21 equal 5 delta x, equal 5 delta x. All right, so next one, let's see, P21. So again, a minus, okay, minus 1, which is 0, minus 1, 0, 0, blah, blah, blah. Okay, and then what's the other one? It's P2, 2 plus P2, 2, okay. And this is equal to P2, 2. Let's see, where is P2, 2 here? Okay, the 0 and 1 and zeros. Okay, let's do one more. Let's see, P31. What happens with P31? We get the same here. Let's see, 0, 0, minus 1, 0, 0, 0, 1, 0, okay, so now you see there is a pattern. There is a main diagonal and there are some off diagonals. Okay, but this is, these are just the rows that correspond to the boundary. Okay, that's why they are, you know, not not the general Poisson matrix that we form. So now, for the inner nodes, we will get exactly that. So let's see. So the inner nodes, let's see, P12. What happens with P12? Okay, let's go back here. P12. Okay, what should we do with P12? Yeah. What should we do with P12? P1, 2. Is it, does it follow this big equation that we wrote? E1, 2?
We have not implemented the boundary condition along the x edge, isn't it?
The x edge being, wait, what is the x edge? You mean bottom boundary?
There's a boundary condition that dou p by dou x is 5 in the x boundary, isn't it?
No, dp by dx is 5 at x equals 0, which is the y boundary, right?
Sorry, okay.
And what we wrote was exactly this, right? dp by dy is 0. Yeah? So that's why we have zeros on the right hand side. But you're going in the right direction. Now, if I talk about this point, that's exactly this boundary condition.
Yeah.
dp by dx equals 5. So, for the first point, we have dp by dx is equal to 5, which means you can write E1, 2, well, actually P2, 2 minus P1, 2 over delta x equals 5, right? Okay, so this is still not an inner boundary node. Okay, so we still don't have the nice p2 comma 2 is plus 1, so it's 0, 1. And then on the right hand side we have 5 delta x 0, 0, 0. And let's see, where do we get p1 comma 2? P1 comma 2 is, oh, okay, this is minus 1. Okay, everything else is 0 in this row. Okay, now this is actually an inner node. So for this we can use the full formula, which is p3 comma 2 plus p1 comma 2 minus 4 p2 comma 2 plus p what 2 comma 3 plus p2 comma 1 equal f2 comma 2 times h squared. Okay, so let's put that in here, which is f2 comma 2 times h squared. Okay, and then we have a minus 4 with self, so this is a 0, minus 4, and plus 1 with the 1 on the right, plus 1 here, oh, plus 1 on the left also. Okay, we have 3 diagonals and there will be 2 more coming from up and down. So let's see what's remaining. 2 comma 1, 2 comma 1 comes from over here. So we have a 0, 1, and 0, 0, 0. And there will be 1 more plus 1 on the right hand side because of this 2 comma 3. So this one. Okay. 0, 0, 0, 0, comma somewhere over here. Okay, so, and this will keep following. So we have 2 terms over here, 3 terms over here, 1 term here, and 1 here. And this pattern will keep going for all the inner nodes. Only at the boundaries will the matrix look different. So this is the first boundary, and the bottom boundary will also look different. Okay. So yeah, you can see that this process is very cumbersome for forming this huge matrix. You have to be very careful with all your signs and all your numbers. But this gives you an exact solution. There's no assumptions in here. You're solving the Poisson's equation. Exactly. Well, there is an assumption that the derivatives can be written as that. Okay. But besides that, there's no assumption in the solution. Is this the only way to do this? So yeah, this is a way that makes sense. You form a huge matrix and solve it. But is there not a better way? Well, an easier way. I remember you had mentioned one. Yeah?
Okay, yeah, iterative solve.
Yeah, you can do an iterative solve. Right? This is a steady state solution. But we can pretend that it actually is a time-dependent problem and do something called a pseudo-iterative, pseudo-transient solution. Okay. Okay, let's see. So forming and solving this matrix is cumbersome. And let's say human error prone and error prone. We can adopt an alternative approach. Okay, what is the Poisson's equation we were solving is here. So, lambda squared t equal rho over delta t lambda dot u star star. Okay, so this does not have any explicit time dependence. No explicit time dependence. Okay, but we can reformulate it as follows to get a pseudo-transient solution. Okay, so let's see. Original problem is del 2b over del x squared plus del 2b over del y squared equal f. Okay, and modified looks like del p over del time, del tau. Okay, this is not real time. This is pseudo time. Equal minus del 2e over del x squared. Okay, and this is called the pseudo time variable. Pseudo. Okay, do you know how to solve this? Does this look familiar or very alien?
This looks like the heat conduction.
This is exactly the heat equation, right? You have solved this exact thing in one of your homeworks. You had del time by del t equal kappa del 2t over del x squared plus sine 5x, right? So you have done this in your homework. And now we have the same exact thing. We have dt by d tau, and this in 2d we have two terms, x squared and y squared, and we have a forcing function, as you had the sine 5x. So see, it's exactly the same thing. And how do you get the final solution? Do you, well, okay, first let's discretize this. Okay, let's discretize the pressure equation. Okay, how do you want me to discretize it?
First order in time and second order central difference in pressure for pressure.
Okay, so first order in time, let's say it would be Pn plus 1 minus Pn over delta tau. And you said what?
A central differencing for
Center difference in space. Okay, let's see. So there's no kappa here. We have a minus. Yeah.
Pij plus 1 at n.
J plus 1.
Yeah.
All right.
Minus 2 Pij plus Pij all at n and by del x square.
Your J. All right. So for me, J goes in Y.
Oh yeah, yeah. This is del y square. And
Yeah. What?
Yeah.
All right. Okay, so this is the d2p or dy squared term, and we do the same with the x. We get I plus 1, comma j, minus 2pij, plus k minus 1, j. Okay, so that's,
This would be del x square, yeah.
oh yeah, sorry, del x squared. Okay, so that's minus the whole thing, and then you have whatever the f is fi comma j. Okay, this is actually the whole u star thing, lambda dot u star star. Okay, so yeah, I mean it's exactly the same as you've been doing for your homework. Code Europe, you can plug and play. Okay. Now, question is, what is tau? What is my starting value of tau, and what is the ending value?
Till it converges to a
Okay.
constant value or
So I can just say, let me start with tau equals 0,
yeah.
and then I will have to keep stepping in time till it converges. By converges, we mean the solution does not change in time anymore. Okay, so if you take 100 more steps, or 10 more steps, or 1 more step, you basically get no change in the solution.
You want to get a steady state solution? Is that the?
Yeah, so because see, we introduced this pseudo time variable. So you want to keep solving this equation till the dependence on time goes away, on this pseudo time goes away. Okay.
So, but here, like, for the time step delta t, do we need to consider CFL condition again? Like, will it be similar to delta t we use for Navier-Stokes?
Not the CFL condition, but the stability for the diffusion equation, right? See, mathematically, this is the diffusion equation. There's nothing different here. So yes, the stability condition would still apply. So let's see. Since tau is a pseudo time variable, that we have introduced, we need to solve this PDE to steady state. That is, until the dependence on tau goes away. Which mathematically is basically del p by del tau is 0. Okay, so we can start with tau equals 0 and keep stepping pseudo time until convergence. Okay, and convergence, you can define what convergence means for you. You could say that the pressure at the new step n plus 1 minus pressure at the previous step, and the RMS of this whole thing should be 0, right? So should be not 0, it should be less than some tolerance. Okay, and this would be the error. Okay, error. And the tolerance can be 1e minus 6, 1e minus 8, whatever you want. And the stricter your tolerance is, the more iterations you would have to do till you converge. Okay, everything makes sense? So this is an easier way of solving of actually putting up the solution for the pressure cosine equation. You're always free to form the big matrix and do it that way, but it's simpler to do this. Okay, so now you know what pressure projection is, what these intermediate velocities are in the fractional step method, and you know how to solve for the pressure from the Poisson equation. Fine, this gives you the pressure. Remember what the last step was? We were trying to solve the velocity field in the Navier-Stokes equations. So we managed to solve the pressure, but not the velocity. How do we get the final velocity?
Bernoulli equation, for example.
The what?
Bernoulli equation for incompressible some certain rotation of the.
Okay, so if I give you the pressure, you would do, how would you do that? I mean, Bernoulli equation is P naught equal P static plus half rho V squared. Right? And there is a V squared. You cannot get V and U components individually. So you cannot get the velocity field that way. Makes sense?
Okay, we don't have enough information.
Yeah. So let me write out the questions. We now have the intermediate pressure. We now have the
Energy equation.
field. How do we recover the final velocity, which is un plus 1?
So the final step in pressure projection, using that we can recover it because.
Yeah, so I think somebody, you were mentioning energy
Equation.
So in incompressible flow, we don't solve the energy equation at all. There's no.
It's decoupled.
Yeah, it's decoupled. Yeah.
No. Yeah, I mean, if I'm right, we are still, discussing regarding solving the Navier-Stokes equation. And in the last step, when we had the un plus 1, we could not solve for the pressure equation.
Yeah.
So the pressure equation was solved so that the conservation of mass is followed when we solve for the Navier-Stokes equation. So we can finally put the updated pressure equation and solve the last part or the third step, which would certainly ensure that the solution that we get will follow the conservation of mass.
Right, yeah, exactly. So that's exactly what you were saying. Okay. If you remember, let's see, we split the momentum equation this way. We split the momentum equation. Right, we had said that we get U star, and let me combine advection and diffusion into one, minus a un over delta t equal minus un dot lambda un plus nu lambda squared n. Okay, and I won't discretize this for now. So let's see. So yeah, we said this was our intermediate solution. which must be made divergence free. And for that, we said we would use the pressure. We said un plus 1 minus u star for delta t is basically minus lambda p over rho. Right? And then we had said this gives us the pressure-Poisson equation. The pressure-Poisson equation, which is what we just solved, right? So lambda squared p equal rho over delta t, lambda dot u star. Okay, and what we've just solved for this, we have solved for this unknown p now. Plug it back into A. To get u at n plus 1. Okay, and that's it. That's the final step. You have completed a full step in solving your fluid flow. So un plus 1 is basically u star plus, not plus, minus delta t over rho, have nothing. Okay, u star is known, pressure is known, delta t, rho are known. You can go on to your next step. And then you repeat the whole thing over and over until you're happy, until you reach the final time that you want to reach. Okay, are there any questions at this point? This is the basics of solving the Navier-Stokes equation. There's variations, but if you understand this, you can always build up on it. Yeah.
How do we determine del tau for solving the Poisson equation by using pseudo time stepping? Like, do we keep it as a ratio with delta t? Because here the restrictions would be less, so we can take del tau to be lesser than delta t, the stability restrictions.
Oh yeah, you should for sure keep it less than delta t itself. Let me see. The stability condition, what was the stability condition for diffusion? It was, let's see, nu, but there's no nu now, right? So let's see, nu for diffusion it was nu delta t over delta x squared should be less than 1/2 in 1 V, right? But this you already have to follow because of the diffusion. So yeah, there's no issue. Wait, no, now there's no nu. There's no nu. Okay, this is basically 1. So it's easier because nu is on the order of 1e minus 6.
Yeah.
So yeah, stability will not be an issue when you solve this pseudo time. You should just take delta t to be smaller, delta tau to be smaller than the delta t, because you're doing intermediate steps. Okay. Any other questions? Okay, so yeah, I mean, at this point, you basically know all the steps you need to solve the Navier-Stokes equation. Okay. If you remember, we were talking about how physical problems always require well-posed boundary conditions and initial conditions. Otherwise, there might not be a physical solution. So that is another problem in solving fluid flow. You have to impose boundary conditions on both the velocity and the pressure. Okay. For the velocity, it's straightforward. For the pressure, it's not very clear. Okay. So let's see. Boundary conditions for velocity and pressure. Okay, let's take a very simple, cut through a pipe or a very simple flat channel. Physically, can you already tell me some of the boundary conditions?
U equals 0 at wall,
U equals 0 at wall.
like x, I don't know how you call it.
Both ux and u.
U infinity equals 0. Or,
U infinity, I mean, you mean
no,
is-
at the wall is 0, right? So,
Okay, so you say not U infinity, but U equals 0, V equals 0.
V equals 0.
And there's a name for these. This is called,
No slip and the first one is no slip.
it's called no slip condition.
No slip condition.
And the other one,
Is wall normal velocity is 0 for maybe.
no through flow condition.
Yeah, no through.
Correct? No through flow condition. Yeah, they are simple logical names. Okay? So when we have, I mean, if I just gave you this physical setup, what would you do? You would discretize it first of all. So you would discretize this maybe as a grid shown here. Okay, and then what would you do? Yeah, I just gave you, okay, this is what your channel looks like. Its length is something L meters, and its height is H meters. Give me the solution. Can you give me the solution?
So we need for another boundary condition left and right.
Inflow and outflow boundary condition.
I haven't told you many things, right? What happens at the inflow, what happens at the outflow, right? I haven't told you what the mass flow rate should be or what the mean velocity should be. Without any of these, you cannot give me a solution. All right, so one of the easy boundary conditions for this problem is periodic inflow-outflow. Okay, this is a very nice, uncomplicated boundary condition. Okay, what do you do here?
The outflow velocity becomes inflow velocity after.
Yeah, whatever goes out here has to come back in here. When I was doing this, when I was green, I would write tons of if conditions. If my j equal j n, my derivative over here, should take right and left, and right should come from the first one. So, there's 10 different if conditions. What is a better way of doing this when you write code? Ghosts, yes. So let me see. I will just use a few points just to keep things easy. This is my upper wall. let's see, let me say I will use only these points for discretizing. Okay, what we do is we create something called ghost cells. And so if you know you had a matrix where you store u comma b for the inner nodes, you just expanded one left and one right. If you need, okay, for instance, if over here I want to compute my derivative, first order derivative, I need stuff on the right, stuff on the left. If I were to use something that was higher order, where I need one left and two right, then you need more ghost cells. Okay? So let's stick to the simplest case, where you need just one neighbor on each side. In which case, this setup works. Right? Okay. What do I do now? Ghost cells, yeah, fine, but they're empty. So let's go a little slower here, because many of you have probably not seen this before. Just as you discretize your one-dimensional rod using many points, we have discretized our two-dimensional setup using different points. And now we are saying we have a periodic boundary on left and right, which means when I'm over here, I will need information to the right, which should actually come from here. Okay? So what I can do is I can take this data and copy it over here. And the same thing on the other side. I can take this data and copy it over there. Sometimes you have to be a bit careful. If you have a sinusoidal initial condition, this is exactly equal to that. So in that case, you would copy the inner one, right? Not the last one. And this copy you have to do once and then you forget about it. True or false?
False.
False. What do you need to do?
Just repeating until.
You have to keep repeating this copying operation over and over again. When you solve the flow inside the channel, the values here will change. The values here will change. So at the end of your computation, you basically take this whole column and copy it again. Okay? And you have to do this at every step. All right, now, in this setup, when I solve my Navier-Stokes equation, what should I do? I should start with the solution of this node. True or false?
False.
False. Why?
It's boundary condition.
It's a boundary. It's a known velocity here. U and V are 0. We don't need to solve for this. Don't need this. Not this. Though, if we were to use this discretization, you only need to solve for the inner nodes. Okay. All right. U is known, V is known. What about pressure? Okay, so let's see. V known. We know the VC for U at the walls. Yeah. What about pressure? Physically, what happens at a wall?
Stagnation pressure.
Stagnation pressure, yes. But
So
where do we get that from?
So we can put in U0 at walls in the Navier-Stokes. derive an equation for del P by del Y or del P by del X?
Yeah, so, again, you might think that here we have stagnation pressure, where we can say B static plus half rho B squared. But that's not strictly true, especially because we are using this time splitting, where our pressure is a pseudo pressure. Okay, I wish I had brought my other notes, but fine. Let's see, we wrote it somewhere here. Where did we write it? Okay. Yeah. Okay. So, see, we are using pressure to enforce the continuity condition. So that's why some people refer to it as pseudo pressure. And any boundary condition you impose has to be consistent with this. Okay. So we can actually start using this A equation to figure out what the boundary condition should be at the wall. Okay, so we can use the what do we call it? The split. The equation from the fractional step. Un plus 1 minus u star over delta t equal minus lambda t over rho. Okay? And we dot it with the wall normal. So n would be the wall normal. You can even do it along the tangent, but wall normal is slightly easier. Yeah, sometimes I write a little too fast, so tell me if you miss something. All right, so what do we do next? We just take the dot product and the insides become u n plus 1 dot n minus u star dot n over the p minus lambda p over rho dot n. Do you know something about any of these terms?
Yeah, V would be 0, u star dot n hat.
V would be 0 for this?
U star dot n hat would give me wall normal velocity.
Okay.
And that is 0.
Okay, so so this is an intermediate solution, right? This is not a physical value. Let's first take the physical value. U at n plus 1 dot n has to be 0. If you're confused about n, if I have a wall that is horizontal, this is n, the normal vector. It would just be a 0, 1, right? So what happens at the wall? U n plus 1 is,
Yeah.
physically it has to be 0. So this term goes to 0. 0 at wall. But U star may not be 0 because it's an intermediate solution. We can actually take a look at what happens with U star. Okay. So, and nabla p dot n can be written as dp by dn. Well, that's the general case, and in this case, we just have dp by dx I plus dp by dy j dot 0 I plus 1j, which is equal to dp by dy in this case. Okay, fine. So let's see. What do we get? dp by dy is rho over delta t, and u star dot n hat will be
V star.
b star. This is u vector star and this is b component. Yeah, go ahead. Okay, and no, this is component number 2 of the intermediate solution. Solution u vector star, which cannot be guaranteed to be 0. Okay, and we can actually see that. Okay, let's see. Where is my other equation? So, if we go back to this is how we figured out what u star should be. So let's use that. See that using as follows. U star minus u, and this is the split of the Navier-Stokes over delta t minus u dot lambda u at n plus mu lambda squared u at n. Okay. All at wall. So at wall, u dot n is 0, which means we can get rid of this term, we can get rid of this term. Can I get rid of anything else? Did I set this to 0?
It's very small.
It's what?
It can't be. Yeah.
Very small negligible.
But yeah, at the wall it should be del square u by del x square.
Have you seen this profile before? This is basically what the velocity at the wall looks like. And its second derivative is not 0 here.
Yeah.
Even if it's a parabolic profile, the second derivative is a constant. Okay. So we cannot guarantee that the second derivative will be 0 at the wall. So let's see. So yeah, what do we get? And okay, we only care about we need only the B star component equation. So we have B star equal mu delta t del 2vn over del x squared plus del 2vn over del y squared. So you cannot assume that the second derivative in the y direction is 0, but this is a fair assumption. That's actually an assumption we use when we derive the equation for the boundary layer. Okay? So fine, now we know what V star is, and finally we have our pressure, Neumann condition for the pressure. Okay? So now we finally have the Neumann pressure condition. Neumann pressure BC, which is del P by del Y is rho over delta T B star, which is rho over delta T nu delta T del 2 B over del Y squared. Make sense? Yeah, so that's one way you can derive and impose the boundary condition for pressure at a wall. Okay, sometimes people assume del 2Vn over del y squared equals 0, which implies del P over del y is 0 at wall. But this is not true strictly. Okay, so let's see, where is my... Okay, so remember, we were talking about this channel, and we've just figured out U and V and pressure boundary condition on the wall. What do we do at the inlet and outlet? It's a periodic inflow and outflow.
Oh, pressure.
Yeah, everything has to be periodic. Would we need to derive equations for this? When you impose a periodic boundary condition, you actually don't need to solve any dP by dx or dP by dy or dP by dy. When are the boundary conditions used? It's at the edges because you don't know what's on the right hand side. But now you know what's on the right hand side can be copied from here. So we don't need to do anything special at the periodic boundary. Okay, so now you have all the information you need. Well, I must give you the initial condition also. And at that point, you have all the information you need to be able to solve this problem. Any questions?
So del square U by del x square would be 0, right?
At the wall.
Yeah.
Yeah, that's an assumption, yes. In the boundary layer, that's an assumption.
No, but for the U, not the vertical velocity, but that would be 0.
Yeah,
It's not 0.
so
Only del 2 U by del y square would be non-zero. But,
you say it's not 0, why?
That's a U over Y, right?
This is V over Y.
Also.
This is d2v dx squared, d2v dy squared. In a flat...
For example, the first one, because we consider a developed flow, so with X is not changing.
Yeah,
So
but
this is a very good assumption. But the Y is changing. In the boundary layer,
yeah,
it's changing.
the
Physically
question
it's
was,
changing.
this is the V component of velocity. What happens to the U component? Okay, so it's exactly what you were saying. On a flat plate, in the boundary layer, you assume things don't change in X very fast. Okay, so you can do the same for U as well. d2U over dx squared would be 0.
Yeah.
But Y would not be. This is actually the profile for U, right? d2U over dy squared is non-zero. B is not as straightforward. It's more complicated. Right, so we're saying the same thing.
But mathematically, I mean, physically, yes, but mathematically, that could be.
This could be large.
I don't know. Is a term, so.
No, it is a non-zero term. Physically, we know this term will be very small. That's why we can make this approximation that it is close to 0 compared to the other one. Okay, the other one will definitely have a very finite non-zero value. Okay, so that's a good enough approximation that things don't change in X very fast inside the boundary set. That was the question?
Yes.
All right, okay. Any more questions? I know all of this must be new, so you know anything you're confused about at all. You actually have to solve all of these steps for the final project. So yeah, make sure you understand each of the steps. Okay? All right, so we have a few minutes and we can talk about irregular boundaries. Here we have a very nice problem. We have a nice rectangular setup and we can form this nice rectangular grid. What happens if we have something that is curved? Okay, what if we are trying to solve? So, irregular boundaries. What if we're trying to solve what flow across a cylinder looks like? What do we do? See, imposing the boundary condition is always a problematic part. And if you have a curved boundary now, where do you impose the boundary condition? The grids that we have been working with look like this. Okay, we would again discretize the whole domain and form this nice grid. Okay, but now we have grid points that are inside the wall. Let's say the wall of the object. And we have points that are just touching it. We have points that are, that's not a point. Is it clear? I mean, we're just taking our full domain, discretizing it again. Some of the nodes are occupied by this obstacle, which in this case is a cylinder. In 3D, it will just be a long stick. And we're looking at a cross-section. What do we do now? We again have to go through the same steps of worrying about what pressure condition, boundary conditions to use, what velocity boundary conditions to use. Okay. So, what do we do?
Making a smaller size, the node.
All right, you want to make the grid smaller.
Around the cylinder.
Fine, let's do that. So, let's see. Let's see, we can try smaller cells. All right, let's see. So, fine, want to have smaller cells. Okay, let me zoom this over here. Did your problem go away?
No, we should define a curvature function for the wall.
It doesn't remove it, of course, but the error will be,
Yeah, it is.
I mean, reasonably can be,
So
it's much better than coarse mesh.
yeah, the decreasing the grid spacing makes your solution more accurate, but this same exact problem stays. Our surface is curved, but our grid is squares or rectangles. One solution is make the grid conform to the surface of the object. Okay, so those are called grid body fitted grids. Body fitted grids. Okay, so if I have a circular object, I would create allegedly circles and then radii. Okay, and now my new grid points are these. There, 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 there. And now in terms of imposing boundary conditions, this is not very different from the flat surface we were looking at before. You would impose u equal v equal 0 here. You would impose dp over dr, r is the radius, equal something, which, similarly as we had derived before, dp by dy equals something. Okay. If you have something that looks like an airfoil, you would have another body conforming grid. Okay, and again you have the nice property of having cells that lie on the surface and they are not being intersected by the surface in a very strange manner. All right, so this, and now we have, instead of a delta x, we have a delta c and a delta eta maybe. Okay, so instead of dx and dy, we have these new variables. And we can transform from between dx, dy, and dc and d eta. And there's some mathematics involved in there, but it's doable. So all our problems are solved, and we can always use body-fitted grids, right?
But we have to transform the equation as well.
Yeah, that's true. All our equations are written in x and y. Now they have to be transformed to c and eta. Yeah, but we can do that, and once we do that, it's done. But, yeah.
Can we define the connectivity matrix?
Whoa, all right, what is the connectivity matrix?
I mean, we will define which cell is the which cell's neighbors and which cell has to...
No, so, okay. You're talking about saying this point knows all of its neighbors, the next point knows all of its neighbors. That's not necessary here.
Mm-hmm.
That is necessary when you have an unstructured grid.
Yeah, unstructured.
Here you can still say, okay, if I go from C equal 1, 2, 3, and eta equal 1, 2, 3,
Mm-hmm.
you still have some sort of structure. That's a good point. I didn't think about telling you that. All right. So there's also something called a completely unstructured mesh. Okay, where let's say you have the airfoil, and you would discretize it using, let's say, triangles. Okay. Oh, I don't want to draw too many triangles. Let me pull up an image on the laptop. Airfoil, unstructured, grid. Where? Oh, yeah, this is exactly what you were talking about. Yeah, so with these unstructured grids, this keeping track of I equal something, j equal something becomes much more cumbersome. It becomes almost impossible, especially when you have different sizes of cells. So in that situation, you would keep track of who is my neighbor, okay? And I will do all my finite difference by talking to my neighbors. Computationally, this is a huge drawback, because now we don't have this nice vector where we can run through it, or a matrix where we can run through I and j very easily. But every time I want, what is the derivative over this point? Okay. The first thing you have to do is loop through everybody and find out who your neighbor sets are, and then figure out what is a good way of computing derivatives in these oddly shaped cells. Okay. So yeah, that's one way that you can get over the problem of how do we impose boundary conditions on the surface of curved bodies. But there's many issues that come with it. Mathematically, it's more involved. Programming-wise, it's much more involved. So people have come up with alternatives called inverse boundary methods, inverse interface methods, or penalty methods, where you can use this nice Cartesian grid, squares or rectangles, and still be able to compute flows on curved surfaces. Okay, so that I think we can talk about next time, because we have 3 minutes there. Any questions in the meantime? Okay, next project is up. It's due soon, so please get a head start on it. And email me, come to office hours whenever you need. Okay, and I'll see you Thursday.
Look, I see.
Right.
How's it going? Good, how are you? Yeah, I'm alright. I think it's hard for a few months. Was doing better, but I have to set an alarm on sit too long. Like sitting for a whole class. Yeah, besides that. How's it going? How's the meeting? Yeah, did you go to course there? Is that where you're going? That's good for you.
I eat and then we can.
I think they. Yeah.
You can start. No?
Yeah. I'm trying to think of what the cheapest could be.
Let's say
Is
2.
it walking distance?
Two.
Maybe the Beach Bar and Grill, but it's all expensive
Or-
here.
You have your laptop.
Yeah.
But
Yeah, that's for sure. Have you started on the project yet?
And in my laptop, I can
It's-
install software.
It doesn't seem too bad so far, but I've only put like an hour into it, so we'll see. How much it-
No, to SSH from my office.
We can SSH.
Come to the office. Because there might be
Two.
one that to come today, but they didn't say when.
It would be nice to have someone to talk about it, but. I just got a new phone this weekend, so I'm still getting used to it. Yeah. I wanted to get the newest